Yes, so we are recording and are very happy to have Ingo with us today, who will tell us something about a very important topic on the QCD landscape, namely deep inelastic scattering. Ingo, you're not sharing your slides at the moment, but
I can share them now.
Did earlier, so yes.
Sharing. Now let me see whether I can go to full screen mode.
Yes, that looks very good. I don't know how you want to hold it, whether the students can just raise their hands in between the lectures. You will get a sign popping up on your screen so that you know that someone has a question, or whether you want to leave them to the chat and or to the end. What is
No. Please ask questions. I have a question. I don't see my cursor. So what can I do to?
I don't know. So one thing, when you share one window only, it might only share that window without the cursor. And now I see the cursor now.
Yeah, okay, but now I don't share. I'm not in full screen mode.
No, that's true.
Is it okay, or?
And what isn't there? Is there something like a laser pointer option in Keynote, which when you do the presentation again?
I can try to share not a window, maybe the entire desktop. Whiteboard. Oh, no, that's probably not what I want. No, that's not what I want. Oh yes, maybe this is what I want. No. Okay, that doesn't help either. Okay, so I do without cursor then. Okay, so let me go back to this.
Maybe any Mac users have further ideas on having something like a laser pointer option. I thought there was something like this when you do the presentation, but I'm not a Keynote user, so I don't know myself.
Okay. All right. So
if you go to the bottom of the screen, do you get some kind of a menu or so?
No. Bottom of the screen. And we can also reduce this. No, I don't. Pause, share, annotate, remote control, more options. Pause online. No.
Okay.
Okay, so I don't know. Annotate, mouse. Maybe this is what I want. No. Okay. Anyway, so I just start and try to figure out later.
Okay.
Good. So welcome everybody to this dedicated lecture on deep inelastic scattering. I mean, Davis and Soper already covered it in a bit. And so before I start, some literature. So this lecture has profited from largely from the textbook by Halsen and Martin, Quarks and Leptons. Another useful textbook is, of course, the pink one by Ellis, Sterling, and Weber. I also profited from previous DIS lectures at CTEC schools by Fred Olness, and a lecture on DIS given by François Gélis in 2006. And there are, of course, many other textbooks on QCD, which cover deep inelastic scattering, like the one by Muta, or there's a book by Field on applications of perturbative QCD, and a book by Cheng Li, and so on. But Halsen Martin is my main source. So in the first lecture, I will cover, first of all, the kinematics of deep inelastic scattering, and then we discuss the cross-section for inclusive DIS in the approximation that we only exchange one photon. I quickly say some things on the operator product expansion. So I will do it very quickly because it's only half understandable anyway on a few slides, and I don't want to sacrifice too much time. So I will do it quickly, then discuss where the longitudinal and transverse structure functions come from, how they are defined, and how they are related to the more well-known structure functions F2 and F1 and so on. Then we have a look at charge current and neutral current DIS, so including exchange of weak bosons, deep inelastic scattering with weak bosons. Then we come to the discussion of Bjorken scaling, and then we have to see whether we have no time left, or if there is still some time, I will start with the Patton model. Otherwise, tomorrow, within where we end here, we will continue then tomorrow. Okay, and I will not cover certain interesting topics, but for example, how to do deep inelastic scattering, including massive quarks or target mass corrections, QCD studies with neutrinos. I will not cover polarized deep inelastic scattering, and also an interesting topic in principle in view of the electron-ion collider. What happens if we have actually targets of spin 1 or even bigger, compared to deep inelastic scattering of protons, which are spin 1/2 targets. So all this I won't have time to cover. So let's start with kinematics of deep inelastic scattering. And as said, please feel free to ask questions. I can't see if you have questions in the chat, so maybe somebody can moderate this also. And otherwise speak up. So the fundamental question is, what is inside nucleons? And more precisely, how does a nucleon look like if it is probed in high energy reactions? And so the basic idea to study this question is to smash a well-known probe, so for example electrons on a nucleon, and then to see what is produced in the final state. And photons are very well suited for that purpose, because we very well know how they interact. So then deep inelastic scattering can then be defined as the collision between an electron and a nucleon by exchange of a virtual photon, such that the virtuality of the photon, Q square, is much bigger than the nucleon mass. So that is the deep part of deep and inelastic scattering. And the invariant mass of the hadronic final state, which I denote by X here. It's called W squared, which is the same as the mass of this final state X squared, is also supposed to be much bigger than the nucleon mass squared. So that is the inelastic, and deep inelastic scattering is a deep and inelastic scattering. And we come later to a variant of this by looking at collisions with a neutrino, and then we have exchange of a Z boson or a W boson. So what are the kinematic variables to study deep inelastic scattering? So I'm talking about inclusive deep inelastic scattering, where complete sum over the entire hadronic final state X is performed. So the process is an electron plus nucleon going to an electron plus a hadronic final state X, with the momenta given there in the equation. So we have certain on-shell conditions. We know that the form momentum of the proton squared gives the mass of the proton squared, and the form momenta of the leptons give a lepton mass small m squared, which we usually neglect. And then we measure the energy and the polar angle of the scattered electron, E prime and theta. But often, instead of using the energy and the polar angle, we describe the process in terms of invariance of the reaction. So in this yellow box, there's a list of 4 invariants, which are widely used. So one is a big Q square, which is minus the small q square, the square of the momentum transfer. Then we have the energy transfer nu, defined as pq over the mass of the nucleon, which in the lab frame reduces to the difference of the lepton energies. Then the Bjorken scaling variable x, defined as q square over 2pq. And finally, the inelasticity parameter y, which is PQ over PL, and in the lab frame, this is nothing as a rescaled energy transfer. So EL minus EL prime divided by EL. Okay, and when I talk about the lab frame, this is the old wording. It means the proton rest frame. So the 4 momentum of the proton would be the mass and then 0, 0, 0, which is a lab frame for fixed target experiments. So then there are essentially 2 independent variables to describe the entire kinematics of inclusive deep inelastic scattering. It's clearly, I mean, we have the outgoing lepton L prime. So we have as 3 degrees of freedom, we have the 3 momentum of the outgoing lepton. So we have 3 variables, but the azimuthal angle, the depends on the azimuthal angle phi is trivial. So we are left with really 2 variables to describe the kinematics. So either the energy and the polar angle, E prime theta, or the variable x and q square, or x and y, and so on. This also implies that q square, x and y are not independent. So there is this important relation that q square is s times x times y in the yellow box, where s is essentially the center of mass energy of the process, modulo the masses of the nucleon and the lepton. So, and this formula is very important to estimate which x values are probed. You know the center of mass energy, 2 times the mass times the energy of the lepton beam. You take for y usually 1 or so, and then you calculate x, you estimate x to be q squared divided by the center of mass energy squared. And the invariant mass W of the hadronic final state can also be quite easily calculated. This is in this, I don't know which color it is, box. So W square is then at the end the nucleon mass squared plus Q square over X times 1 minus X. And so the invariant mass W of the produced hadronic system is important for certain discussions. For example, if W is just the nucleon mass, which is the case when X is 1, then we have elastic scattering because the nucleon stays intact. And to have an inelastic scattering, we have to produce at least a nucleon and an additional pion. So W has to be at least the nucleon mass plus the pion mass, and that corresponds to an X value which is smaller than 1. So here on this upper plot is shown the differential cross-section as for a given energy and a given angle as a function of this invariant mass W. I took this figure from Halsen and Martin. And there you see at W equals the nucleon mass, there is this big peak, which corresponds to elastic scattering. So that's the elastic peak. And in reality, it is much bigger. So it has been reduced by a factor of 8.5. So it's really the dominant contribution. Then when you increase W, you come in a region with some resonances. In particular, the first big resonance is a famous delta resonance at 1232 giga-electron volt. And then there are more resonances. And above 1.8, it starts to be a smooth curve, which corresponds to a continuum of final states. So that's a so-called inelastic region. Knowing that at W about 3 GeV, there are the charmonium resonances, and at W about 9 GeV, there are the bottonium resonances. But typically in an analysis of deep inelastic scattering, one often imposes a cut on W to ask for W to be bigger than, say, 1.8 or 1.6 giga-electron volt to avoid these first resonances. So then one can also have a look at the phase space in the new Q-square plane. So here's another figure from Halsen and Martin. on the y-axis is q square, on the x-axis is in elasticity parameter y, and you see that q square is proportional to y, so it's a linear dependence, and the slope of the linear curve is 2 times m times e, so the center of mass energy squared times x. So if x is 1, the slope is steepest. That corresponds to the elastic scattering. If x is 1/2, we reach at y equal 1 the point q square equal me. This is this dashed line. And the smaller x is, the less steep the curve is. And in addition, if you work out the kinematics and impose that W is the mass of a resonance, say the delta resonance, you find then that Q square is the nucleon mass minus the resonance mass squared plus 2mey. So we again have this slope 2me, the slope with x equal 1 times y, plus a constant. So which is negative. So we shift the curve with x equal y parallel for a fixed W. No, fixed W curves are parallel to the W equal m curve here, and that is then describing a resonance. So then one can separate the phase space into several regions. So first of all, the resonance region, where we set W about 1.2, 1.3, 1.4 giga electron volt, and an inelastic region for W about 1.6 giga electron volt or more. And this is shown by this red line, which is separating the resonance region from the inelastic region. Then one can also slice the phase space into a deep and a shallow region by this blue line. So the blue line is a constant q square, here q square of 1 GeV squared. And what is above it would be called deep, and what is below it would be called shallow. And then, as I said, in global analysis of DIS data, often the cuts q square bigger than 4 GeV square and W bigger than 3.5 GeV are employed, for example. And so a W cut, if you look at the formula, removes the large X region. And the Q cut removes the smallest X because Q square is SXY. And if this has to be bigger than something, that imposes a limit on X, which can be too small. So then, if you look at this phase space with increasing energy, one can convince oneself easily that the deep inelastic region actually dominates in the phase space at some point. So, and that is, this discussion is interesting, for example, if you look at neutrino cross sections at atmospheric neutrino energies. So on the upper plot, you see the blue line is the atmospheric neutrino flux. So there's on the y-axis the flux as a function of the neutrino energy. So with energies of GeV order or low GeV order, we have actually the atmospheric flux, which is quite well in the region of several long baseline experiments, like the flux from the K2K experiment or the Minos flux or the Minerva flux. They are all in this area. And the future long baseline experiment Yoon will also have a flux in this area, because if you look at the neutrino oscillation formula, which has a sine square length of the baseline over the energy, L over E, times the mass difference, delta M square, with a given length of a couple of hundreds of kilometers, and these atmospheric neutrino energies, you probe exactly the mass range of neutrino oscillations, of atmospheric neutrino oscillations. So now on the lower plot, on the same scale of the energies, you see the charge current neutrino cross section divided by the neutrino energy. And then if you look at large neutrino energies, the dotted black line takes over. So that is really then the deep inelastic cross section which dominates everything simply because of the phase space. But in the region which is interesting for these neutrino long baseline experiments, you see that all three contributions, so the green curve, which is the resonance production, and the red dashed line, which is elastic or quasi-elastic scattering, they are all important. They are all relevant, and so you need to understand these cross sections quite well in the next generation of neutrino oscillation experiments to really extract the parameters like CP violation in the mixing matrix and so on. So you need to know all these cross sections well, in particular also the deep inelastic one, and how these different things match together. Now, how to define what is resonance and what is deep inelastic, and how to match these things together. So first homework problems, work out some of the kinematic relations. Some of these exercises are from Halsen. And so for example, work out Q square in terms of the energy and the angle of the scattered electron, and show that there's a formula for Bjorken X in the target rest frame, and so on, to get familiar with the kinematics. Okay. Are there questions so far? Or if not, then I will go on and discuss how the cross section for inclusive deep inelastic scattering is calculated. And all this discussion is very general, so it will only be based on basic symmetries of the theory and Lorentz invariants. So the only assumption that I make in the following discussion is that I consider only one photon exchange. So if you want to include contributions from two photon exchange, which is of course suppressed by recoupling, then this formalism would need to be extended. But that's a small correction, of course. So let's consider now inclusive DIS, where we perform a sum over all the hadronic final state X. And for definiteness, we look at electron, nucleon going to an electron with form momentum L prime, and hadronic final state X with form momentum Px. Then the amplitude of this process can be calculated as a current-current interaction. So we have a leptonic current small j, a hadronic current capital J, and then a 1 over Q square factor due to the photon propagator. And then the leptonic current is, of course, well known perturbatively in QED. Now we just take our QED Feynman rules. It's U bar gamma mu U. And the hadronic current, on the other hand, is non-perturbative and depends on the final state X. So we can just write it as we take the current operator, which is of course known as quark gamma mu quark, and roughly speaking, and then we just write down the matrix elements. We start with a proton state, and the final state is some X, and so then one needs to evaluate this amplitude. But for the cross section, actually we need the absolute square of this amplitude. And this can be written as a contraction of a so-called leptonic tensor with a hadronic tensor W mu nu. So you see this figure. On the one hand, we have on the left the amplitude A and the complex conjugate A star. And the product of the two is the square of the matrix of A. But on the other hand, we can separate this cross-section along this dashed horizontal line. And the upper part is the leptonic tensor L mu nu, which is calculable in perturbation theory. And then the lower part is the hadronic tensor, which we can't calculate in perturbation theory. And then we need to include the propagator and couplings, and that is essentially then the cross section. So here's the entire formula for the cross section. So there's a flux factor F, the Möller flux. Then we have the matrix element squared AX, here spin averaged, and we integrate over the full phase space, which is split up into a phase space dqx for the hadronic final state, and then the phase space for the outgoing electron, and a sum over all the final state x is implied. And when I write a sum here, that includes, of course, also the integration over. So it's a sum and integration over the phase space. So a sum over all possible final states. For example, a final state with a nucleon, 2 pions, a kaon, or a final state with 20 pions and 10 lambda baryons. So all numbers of particles and sorts and types of particles need to be included in this sum. So the expressions for the phase space are the usual ones. So we have a 4 momentum conservation factor, and then this relativistic phase space factor d3p over 2 times the energy. I guess that is well known. And then the amplitude is a product of these 2 currents. So in red, the hadronic current, in blue, the leptonic current, and then the coupling, E square, and the propagator factor, Q square. And the complex conjugate over X is written on the right side, according to the rules of quantum mechanics, right? So a bracket, when you take the complex conjugate, you exchange the states, and the operator has to be replaced by the Hermitian conjugate. Okay, with this, we then have the expression for the leptonic tensor, L mu nu, which is a standard exercise in particle physics. So if you do the Diracology of this expression for L mu nu, you find a Dirac trace, which can be easily evaluated, and you get this expression in the 3rd line of the blue box. And for the hadronic tensor, which is then defined as the rest of everything in the cross section, so a sum over the states, an integral over the phase space x, the 4 momentum conservation, and then the product of matrix elements of 2 hadronic currents. And we spin average this in this case. And note that the factor 4 pi is a convention such that the hadronic tensor is dimensionless here. And for example, Halsen and Martin use a factor of 4 pi m. And then in this case, the hadronic tensor would have a mass dimension -1. So then, since we cannot calculate the hadronic tensor, at least not in perturbation theory, what one can do is we can parameterize our ignorance. So we write down the most general covariant expression for the hadronic tensor, W mu nu. And taking into account, of course, symmetries like current conservation, parity, time reversal invariance, and so on. So how do we do this? Our available quantities are the metric, then the 4 momentum of the nucleon, and the Q, the 4 momentum of the exchange boson. And then in the green box, you can write down all possible tensors of rank 2, which you can form out of these quantities. And there are 6. Then you multiply each of these tensors with some structure function, W1, W2, W3, which still parameterizes our ignorance of everything. So we just have taken out the Lorentz structure out of the problem. And the structure functions, Wi, can only depend on Lorentz invariance then. So on P square, Q square, and PQ. So here's an W mu, and when you then look at it closer and do the contractions with the leptonic tensor, you will see that the part with W6 does not contribute to the cross-section at all. And the parts with W4 and W5 give contributions to the cross-section which are proportional to the lepton mass squared. And since we in mostly all cases neglect the lepton mass, they also don't play a role. And this is a reason due to current conservation, or so that if you contract the leptonic tensor with Q mu, this is proportional to the lepton mass squared. And if and in the electromagnetic case, it would just be 0 due to current conservation. But even in charge current DIS with W boson exchange, the current would be conserved if we neglect the lepton mass. And otherwise, it's not exactly conserved, but you get terms proportional to the lepton mass squared. So parity in time reversal symmetry implies that W mu is equal to W nu mu. And that implies that W3 and W6 have to be 0 for parity conserving currents, like the electromagnetic current. So this type of game is then used to reduce the hadronic tensor a little bit. So then due to current conservation at the hadronic vertex, you get relations between some of the structure functions. So W5 is related to W2, W4 can be related to W2 and W1. And if we impose current conservation plus parity symmetry, we are actually left with 2 independent structure functions. And that is the form given in the lower yellow box. And that is the tensor you usually see in particle physics classes for the electromagnetic current. So with this, we have everything to calculate the cross section. So we have the leptonic tensor, we have the hadronic tensor, all summarized in the light blue box. And then doing the contractions, L mu nu times W mu nu, you can easily find this expression, which is given below the box. And you can evaluate the scalar products also in the nucleon rest frame. And at the end of the day, you find the cross section in the nucleon rest frame, which is given in the yellow box. So that is, I guess, very well known. So then it is customary to define scaling structure functions. So you replace W1, W2, W3 by structure functions F1, F2, F3, where the relation between them is given in the yellow box, so that they are dimensionless quantities which approximately are independent of Q square. So they are scaling, as I will discuss later. And then one can change variables from the energy and the solid angle of the outgoing electron to X and Y, and replace the W's by the F's. And then you can write down the cross section d sigma dx dy. And there's a formula which you should try to reproduce, because you also find it in the particle data booklet, for example. No? And those are nice exercises that you reproduce these equations which are given in the particle data booklet. So more homework problems. So there's an exercise on the phase space. Yeah, just as I said, derive this cross section for d sigma dx dy. And yeah, and verify that the hadronic tensor in terms of the structure function F1, F2 can be indeed written as it is written there in the lower box. So now there's another homework problem which is a little bit more extended. Starting from the definition of the hadronic tensor in the first line of the yellow box, You can then replace the four momentum conservation, so the Dirac delta distribution, by a representation as an integral over the exponential function. You can use that the space-time translation of an operator in quantum mechanics is generated by the four momentum operator in the way I have written up. You use the completeness relation, that when you sum over all intermediate states X, that this has to close to the identity operator. And then you should be able to verify these four forms for the hadronic tensor. Okay. So now let me quickly say something to the operator product expansion. So the starting point is the optical theorem. So graphically, this on the left side, this red blob is the hadronic tensor W mu nu is essentially the square of the amplitude, which is represented by the red blot, and this dashed line cutting this amplitude means that this intermediate state is on its mass shell, yeah? And that is just a graphical representation of the W mu nu. Now, if you remove this dashed line, you arrive at the forward Compton amplitude. And then there's, due to the optical theorem, there's a relation that the cutted diagram is related to the imaginary part of the uncutted diagram. And so that gives us a relation that the hadronic tensor is 1 over pi times the imaginary part of the Compton forward scattering amplitude T mu nu. So why is this interesting? So in T mu nu, you see there's a matrix element of a time-ordered product of two currents, J mu at x and J nu at 0. So there's a product of two currents. Now, if you analyze due to this oscillating phase e to the iqx, if you do the analysis, and I refer you to the textbooks by Cheng Li or by Mutter, that this is dominated by contributions near the light cone, x square about 0. And then the operator product expansion introduced by Wilson in I think 1969 is then a sort of Taylor expansion of such a product of currents. So if you have a product of currents, J or of operators at a position x and another one at a position 0, and if x becomes small, or here x squared becomes small, then you can write it as a sum of local operators, which only which are defined at one position, 0, times some coefficients c, which are Wilson coefficients, which contain the behavior in x, so that it still depends on x squared. So without going much into detail, just two things. First of all, this kind of Taylor expansion for the product of currents is independent of the target. Okay, so that is the first thing. And the second thing is that this OPE implies a factorization into Wilson coefficients, which depend on x square, or if you go later to Fourier space, which depend on q square only, and matrix elements of local operators, which more or less then correspond to parton distributions in the parton language. So this OPE implies a factorization. And then just something to introduce the word twist. So these operators OI depend on what I just says that there are several operators which can be composed out of the quark and gluon fields. But tau is a label which defines the twist. So that is defined as a dimension of this operator, of the local operator, minus its spin. Yeah, we have, without saying it, we are looking at operators with definite spin n, because we have n Lorentz indices, and we take symmetric traceless versions of it, so that it's really operators of definite spin. So we know the spin of this operator, which would be n, and we can calculate the dimension, the mass dimension of the operator, and the difference is called the twist. And this is important because if you look at the Wilson coefficients, naive dimensional counting, they are near the light cone given by x to the power twist minus 2 times the dimension of the currents. So the smaller the twist is, the more the more singular the term is. So the more important the contribution is. Huh? So overall, the exponent will be negative, and then if we have a big twist, it can even be positive and not be singular at all. But the dominant contributions come whenever the tau is as small as possible. So the leading term has lowest twist. And so what we often do then, and also in the Pareto model, we only look at the leading twist 2, which gives the dominant contribution to this series. And higher twist terms then correspond to operators with tau bigger, and that translates in, if you do the analysis, into terms which are suppressed by powers of q square, 1 over q square, 1 over q to the 4th, and so on. So they will be suppressed with respect to the leading twist term. So I think that's basically all I want to say about the OPE. So there's a, no? It's frozen. I can't move my slide.
I also don't see it moving on the shared screen. So.
Yeah, I still can hear you. That's good news because I saw my computer crashed, but I can't neither go out of my slides.
If you stop sharing, say anything like.
Yeah. Oh, no, it's working again. Okay, good. Okay, so that's basically all I want to say about the OPE. I mean, just summarizing quickly, then there's a lot of manipulations if you look at the few pages in the textbooks. So where you then really evaluate the forward Compton amplitude T mu nu for twist 2 operators, and Fourier transform of the Wilson coefficient will appear, and so on and so on. And then, in addition, you can write a covariant expansion for the T mu nu as you did for the W mu, and then use the optical theorem to relate the W's to the T's via dispersion relations, which then lead essentially to Mellin transforms. And at the end of the day, you find then relations that the Mellin transform integral dx x to the n minus 1 of the structure function is given by the Mellin moment of the Wilson coefficient times the Mellin moment of the matrix element of the local operator, which will be the Mellin moment of the Pareto distribution functions. Okay, so just to give you the idea where this forward scattering amplitude T mu nu enters, where it plays a role, and that you can do based on this an entire analysis using operator product expansion and get results for the structure functions. Okay, now let us return to what it actually means when we talk about longitudinal and transverse structure functions. So as I said, our hadronic tensor in the upper yellow box is given by some part with F1 plus another tensor structure with the structure function F2. Now, in order to access F1 or F2, you can define projection operators formed out of the metric and P and Q, such that if you contract this with a hadronic tensor, you get the structure function F1 or F2. And that you would maybe do in an actually calculation of a DIS process. So you calculate this using your Feynman rules, and then you use these projection operators to project out the structure function. Now, one can introduce transverse and longitudinal structure functions by contracting the hadronic tensor with the polarization vectors for transversely or longitudinally polarized virtual photons. That is shown on the right side in these figures. So if you take polarization vectors for a virtual transverse photon and contract the hadronic tensor with it, the result will give you what is defined as the transverse structure function. And the same for longitudinally polarized photons. And if you do this, it turns out that the transverse structure function is 2x F1. So F1 is the transverse structure function. And the structure function F2 is then F longitudinal plus F transverse. So, and this is a little exercise, a homework problem in
Ingo, before we go to the homework, if you don't mind being interrupted, I see that there's a hand raised with the question, so maybe we can take that before continuing.
Yes.
Chinmoy, I think you have
a hand
raised.
Am I audible?
Yes.
You are doing this Mellin transformation. Why we need this Mellin transformation?
Now it appears when you want to calculate the structure functions via the operator product expansion. So you see we have this relation that the W mu nu is imaginary part of the T mu nu. And then you have here the expansion in T1, T2, T3, and so on. And then W1 will be the imaginary part essentially of T1. And then you use dispersion relations to relate T1 to W1. And when you evaluate these dispersion relations, you end up at the end with a Mellin transform. So it's a longer, I mean, it's a manipulation over 2 pages in the textbooks. Okay. So the Mellin transform of the structure function comes out of the formalism. And then it turns out that it is related to the Mellin transform of the Wilson coefficient times the Mellin transform of the operator matrix element. It's not introduced by hand that you just do the Mellin transform, but it comes when you relate the T mu nu to the W mu nu via the optical theorem. Okay. That's the best I can say at this level of precision I have given on the OPE. So, okay, so here, as I said, there's an exercise given in Halsen-Martin where you have find expressions for the polarization vectors for transversely or longitudinally polarized vectors. Oh, there's a typo, by the way, for lambda equals 0. So it should be epsilon 0, not epsilon plus minus. And then when you work this out, write down the completeness relation for space-like virtual photons and do the contractions with these polarization vectors, you find that you get FL, and you find that it will be F2 minus F transverse. And the same for the when you contract with the transverse polarization vectors, you get by definition F transverse, and it turns out that this is equal to 2x F1. So that's a nice little exercise to understand where these words FL, FT come from and how it belongs to F1, F2. So now let's discuss a little bit and maybe quickly charge current and neutral current DIS. So it's in principle as before. The only difference is now if you look at the figure on the left, that we have exchange bosons B and B prime. So before we were considering only a photon. So B would be a photon and B prime would be a photon. But assume we include also the Z boson, then we have several contributions. So we have then photon, photon, photon Z, Z photon, or ZZ exchange. And all these four contributions need to be included to the cross section. For charge current deep inelastic scattering, where the exchange boson is a W boson, we only have one contribution where B is a W and B prime is a W. And then the cross section d sigma dx dy will be the sum of d sigma dx dy bb prime. And we need to take into account also B prime different from B in case we have different bosons to take into account the interference terms. And then there's a general expression for d sigma bb prime, which can again be found in the particle data booklet, and which is given there in the blue box. It's again the contraction of the leptonic tensor with the hadronic tensor. And then you have these factors chi b and chi b prime, which take into account the difference with respect to the photon exchange case. So on the one hand, the propagator needs to be modified with respect to the photon propagator, and then the couplings need to be taken into account. And that leads then to these expressions in the yellow box for chi z and chi w. If you just take the photon, the chi is just 1 because we just have the right photon propagator already in blue. And otherwise it needs to be modified by these chi factors. So that is using this general expression, you can then calculate the cross section for general charge current or neutral current DIS. And here would be an example charge current tau neutrino DIS. As I said, this is the only case where it matters to keep the lepton mass of the outgoing tau lepton in the game. So here you see, otherwise the structure functions F4 and F5 would be neglected usually if you have a muon or an electron. So the mass of this with respect to the center of mass energy would be negligible and neglected. But in the case of tau neutrino GIS, one would like to keep the F4 and F5 structure function, and there would be the cross section. And then there are relations at leading order that F4 is actually 0 and F2 is related to F5, which one can calculate. And in the literature, the full next to leading order expressions are also known. And then you can actually see, this is untested. If you calculate this cross section, the charge current cross section divided by the energy on the y-axis as a function of the incoming neutrino energy, the dashed line would be the cross section if you neglect F4 and F5, and the solid line would be the standard model prediction. And this is something that has not been seen or tested so far and could be tested at a future experiment which had been proposed at CERN called SHIP. I don't know what is the status of the SHIP experiment, whether it will come, but this is a place where one could test the structure functions F4 and F5. But anyway, this formula is generally true for neutral current and charge current deep inelastic scattering. So this is then again, I mean, do the contractions and calculate it. Here's some homework problem that the leptonic tensor for BB prime would look like this, and you can try to work it out with the couplings given here. The hadronic tensor is written again, and then you do the contractions and then you can try to find the cross section given here as a homework exercise. So now let's discuss a little bit Bjorken scaling, which is an important result. So let's have a look at elastic electron-proton scattering. And to start with, we look at a point-like proton without spin. We neglect the recoil and we scatter off the electron elastically. And then the cross-section, as you know, is the Mott cross-section, which is the Rutherford scattering cross-section times a cosine square theta over 2 to take into account the electron spin. Now you can say, okay, let's keep the proton point-like, but we include the spin of the proton. And then the cross-section will be the cross-section, the Mott cross-section, times an expression E prime over E, which takes into account the recoil energy of the proton, and an expression 1 plus 2 tau tangent squared theta over 2 due to the spin of the proton. Tau is essentially q square over the mass of the nucleon. Now we can say, okay, let's look at a proton which is not point-like, but really is extended. And that means we have to introduce form factors to describe the hadronic tensor, the hadronic current. And then the cross-section is given by the Mott cross-section times E prime over E. But instead of 1 plus 2 tau tangent square theta over 2, we have form factors. So g e square plus tau gm square over 1 plus tau. And then the tangent square term is multiplied with another form factor, 2 tau gm square. So these form factors are ge is the electric form factor, normalized to 1 if q square is 0, so that we see the charge of a point-like proton. And gm is the magnetic form factor. And these form factors have to be taken from experiment. So they have been measured, and it is known that they are steeply falling with q square. So there's a so-called dipole form, which is in the box on the right lower corner. So before showing a plot showing these form factors, just a short remark. Note that the idea of a point-like strongly interacting particle is rather academic. Due to quantum corrections, we have to generalize the point-like current by the most general current respecting all symmetries of the interaction and introduce form factors. So even in QED, you would introduce form factors F1, F2, Dirac and Pauli form factors, or GE and GM. However, the difference is that in QED, we can calculate them in perturbation theory. Whereas in QCD, for the strong current, we can't calculate those form factors. So as soon as we have quantum corrections, even an electron is not point-like in this sense. And so it's a little bit academic to look at a point-like proton spin. Okay, now let's have a look at the steeply falling form factors. So what do we expect for a point-like particle? And that's a slide from Fred Olness. So we try to resolve a point-like particle, and the cross-section will be just 4p alpha square over q square times 1. No, 4p alpha square over q square just for dimensional considerations, and 1 because we don't see any structure. Now we increase the energy, smaller wavelengths, but since the proton is point-like, we don't resolve anything. The cross-section would be the same. If we further increase the energy, it's the same. No? We don't resolve anything if it's point-like, and the structure function would be the same. So now here are measurements of these form factors. So the electric one, GE, and the magnetic one, GM, for the proton and the neutron, as a function of q square, and you see they are falling off with q square. So it really corresponds to this dipole form I gave before. And that means on the plot on the right, you see that the cross-section as a function of momentum squared really falls down for a finite proton compared to the expectation for Mott scattering, which wouldn't fall off, or at least not very strongly. So, and those results were known in the 60s, and they formed the prejudice that the proton was a soft, mushy, extended object, possibly with a hard core surrounded by a cloud of mesons, mainly pions. So somehow, I guess, the Bohr picture of the atom, where you said, okay, the atom is a small, hard core surrounded by a cloud of electrons, and you just transfer this idea to a proton now, that there is a hard core surrounded by some cloud of mesons, pions, huh? And that then results into those form factors and the steep fall. That was the prejudice. And then the SLAC, Hofstadter had the objective to search for this hard core of the proton. And that's why they increased the kinematic range and did the first deep inelastic scattering experiments. So, as I said, the formula for elastic scattering is given in the upper yellow box. The deep inelastic scattering cross-section, as we derived before, resembles the elastic one, just that we replace the form factors by structure functions W2 and W1. And the idea was that the W2 and the W1 would be steeply falling with Q square. Now on the right, you see the data from an early SLAC experiment. So the cross-section divided by the mod cross-section as a function of Q square. And as you see, the DIS cross-section depends only very mildly on Q square there, whereas the elastic scattering one would fall off very steeply. And that was a big, big surprise. So that led to the scaling hypothesis by Bjorken. So in the limit of high energies, Q squared to infinity, nu to infinity, such that X, the Bjorken X is fixed, the structure functions are actually not falling off with Q square, but they are insensitive to Q square. So this behavior is called scaling, and X is called the scaling variable. And scaling implies that the nucleon appears as a collection of point-like constituents when probed at very high energies. So we don't have one small hard core and then some soft cloud of electrons or pions, but instead we have a back of many, many small grains, which are a collection of point-like constituents. And when you develop this idea, that was developed by Feynman and brought forward. So the possible existence of such point-like constituents was proposed by Feynman, and I think he could explain with a quick calculation overnight this scaling behavior when you have a structure like this, so that you really can explain that scaling observation. And he gave those point-like constituents the name partons. And then the structure of the proton would, when you increase the energy of the probe, the cross-section changes. No, at long wavelengths, we have the cross-section 4 pi alpha square over Q square times 1. You increase the energy, you start to resolve form factors f of Q square. You really increase the energy so that you really probe the substructure at small distances. And you don't have a form factor f, which falls off quickly, but you have the charges squared of these constituents. So no Q square dependence in first order. And that would be then scaling. And experimentally, you see it here. The structure function F2 has been measured at Hera and also at fixed target experiments over wide kinematic range in Q square. So you see on the y-axis is the structure function F2 times some factor 2 to the I to separate the data as a function of Q square. And then you see at x about 0.2, this is this horizontal red line, the data are really constant, they are flat and they don't scale. At small x, you see a slight rise in Q square. So, and at large x, you see that the cross sections drop slightly in Q square. And that is due to scaling violations, which enter when you take into account QCD corrections to this parton model picture. which will come later. Okay, but essentially at x about 0.2, we still have really scaling in the data, independent of q square. And that indicates that the nucleon is really composed out of point-like partons in a certain sense. So here the same is for the structure function FL. So here's a plot with FL and F2 as a function of X. Okay, here you can't see well. On the right plot, you see FL as a function of Q square, and you see that the data are quite insensitive to Q square. And we also note that FL is much smaller than F2, as you can see on the left plot. Okay, I think we have 1 hour, so I don't know. Shall we stop here or?
Yes, I think that's a good point to take the coffee break that is planned. We're running a few minutes late, which is mainly my fault for talking too long in the beginning. But I think we can take a break until 35 past. So let's restart at 11:35. We're gonna get a coffee, stretch the legs, and come back. Relax, and then we could also, if there are any questions that develop from the first part of the. Oh no, sorry, we don't take a break because you're continuing tomorrow. I'm getting confused.
Right, I continue tomorrow, but this evening is the recital session.
So if you're joining for the recitation session, then that's great. Then everyone can also think about questions and come back with them in the evening or also in the morning tomorrow for the lecture.
Okay, perfect.
Cool. Thanks a lot, Ingo. And then we will all reconvene here and have Valerio as a speaker at 11:35.